Alrighty. Hello, everyone. Thank you for coming out to our webinar today. We will begin here in a second. First, I'd like to let you know that we will be recording this webinar, and we will have a Q&A address at the end. And like we said, if you have any questions, please feel free to put that in the Q&A box at the bottom. So please sit back, relax, and enjoy. Now, hello everyone. My name is Jacob Trevithick, and I am an RF component engineer here at Marki Microwave. In the last year, I've been working on the amplifier team alongside my colleague Rob here. I've mainly been working on testing and characterizing amplifier chips and modules, as well as multi-chip active modules that contain amplifiers. Now, today I will be presenting Amplifier Biasing Made Easy. In it, I will attempt to give you some insights into the things that I've learned in my time at Marki, and I will go over some of the key considerations that we think about when choosing the correct amplifier bias levels. I will attempt to simplify some of these variables in a way that helps you choose your correct bias for your application. Now, I will be presenting, at the end, we'll have some Q&A with my colleague Rob here, and I'll let him introduce himself now.
Hey guys, thanks for tuning in. And for those of you who don't know me, my name is Rob Maurer. I've been Marki's resident amplifier designer and specialist for about 2.5 years, a little over maybe. I've been primarily aiming to design extra amplifiers for our catalog, get the catalog off the ground a little bit. First and foremost, I want to have some amplifiers capable of driving all of our mixers that we sell in our catalog. So we've been expanding into different frequency bands, and we've also been trying to improve the selection and variety for our customers' various application spaces. We've been getting into some low phase noise amplifiers and some positive bias only amplifiers and some millimeter wave single octave band amplifiers and some distributed amplifiers. So I'll be commenting throughout the presentation in the Q&A box as you guys ask questions, and I'll come back at the end for a Q&A session for any questions that I can answer. I'll try to answer as many as I can. And for now, I'll hand back over to Jacob. Enjoy the presentation, everybody.
Okay, thanks, Rob. All right, now let's get started. Now, to begin, I would like to introduce some of you to the basics of what an amplifier is. Amplifiers are active devices that increase the power of an RF signal. In order to do this, the amplifier needs to add energy to the signal by consuming some external power in the form of DC supply or bias voltage and supply current. Here, what we mean by RF signal is a high frequency signal that we are trying to amplify. And when we say DC, we are referring to a constant voltage source. Now, amplifiers are devices that are constructed using transistors. An amplifier could only have one transistor in it, or it could have many. This just depends on the application and the design goals. Now, as I've mentioned, amplifiers do require some DC power to function, and how the user decides to apply this DC power has an impact on the performance of the amp. So I'd like to go into some of the main considerations that come into play when you are applying this DC power. Now, there are many considerations that should be made when you're choosing the right bias or bias circuitry. And these variables can be a little bit overwhelming if overlooked, but they can be boiled down to a few simple key concepts. The figure on the right represents many of the factors that go into biasing an amplifier. And although it looks a little bit more complicated, there are just a few things that we want to look out for. Firstly, the power supply provides the current to the amplifier and controls the linearity, but the power supply does add some unwanted noise to the output that we should try to be careful about. The bias setting sets the bias point of the transistors based on the application. Adjusting this setting controls the bias point operating class and the harmonic generation. The bias voltage supply can also provide some noise to the signal path. To help alleviate some of that unwanted noise from the bias and supply lines, we want to utilize some kind of bypass circuitry to provide some noise filtering. This bypass circuitry affects the stability of the amplifier and the switching time. Now, finally, it's important to consider the reliability of the amp. Overbiasing or improper sequencing can cause some damage to the transistors over time if care is not taken. Now, these considerations should be taken for all amplifiers, but there are some differences in the bias circuitry between the different types of transistors that are used in amps. Now, there are two main types of transistors that can be used in amps. These are FET and HEMTs, which stand for field effect transistors and high electron mobility transistors. And we have BJTs or HBTs, which stand for bipolar junction transistor and heterojunction bipolar transistor. At Marki, we tend to use PHEMT and HBT amps. Now, before we get too far, I'd like to define what we mean by supply and bias in this presentation. I will refer to supply voltage as the DC voltage supplied to the drain or collector. And I will use the term bias voltage when referring to the DC power supplied to the gate or base. There are a few things that are common to both FET and BJT amplifiers. They both require DC blocking caps to block DC signals and let RF signals pass through. And they both need RF chokes to block RF signals from entering the supply line while allowing the DC voltages to pass. The difference between the two architectures lies in the gate or base biasing schemes. The FET bias voltage can typically be set with just a resistor, since there's nearly no current flowing into the gate of that transistor. The BJT amplifier, however, does operate with a small amount of base current flowing, so you need to use a little bit of additional bias circuitry in place there. A standard current mirror is what we typically use. Next, we will talk a little bit more about the differences between these two amplifiers. Now, moving into FET-specific biasing, in the context of biasing, there are two types of FETs that we typically see. These are depletion and enhancement mode FETs. Depletion mode FETs are typically operated with a negative gate bias voltage because they have a negative threshold voltage. This means that there is a natural channel formed between the drain and the source when there is 0 volts applied to the gate of that transistor. Because of this, it's usually recommended that you sequence the supply and bias voltages so that the bias voltage turns on before the supply voltage. Now, this is to avoid some unnecessary spikes in current flow through that transistor. The enhancement mode transistors, however, have a positive threshold voltage, so they do not have a channel formed between the drain and the source when there is 0 volts applied to the gate. They need a positive voltage applied to the gate to allow current to flow. So these transistors typically do not require sequencing and only need positive supplies. Now, moving along into BJT-specific considerations, there are a few more things that should be thought of when using a BJT amp. One consideration that we want to make is the possibility of thermal runaway. Now, this is an issue that is caused by the self-heating of the transistor. When the supply current to the transistor is increased, more power is dissipated through the transistor, and as more power is dissipated, the junction heats up. This causes the base emitter on voltage to decrease, and consequently, the current goes up and the cycle continues. To protect against this thermal runaway, a ballasting resistor is used on the base, typically. Another potential issue with BJT amps is that their collector current is exponentially proportional to the base emitter voltage. This means that any small fluctuations in the base voltage will result in large swings in the collector current. So you really need to have some extra circuitry there that makes the base emitter voltage less sensitive to the bias voltage. Now, to achieve this and to solve that issue, a standard current mirror is often what we use to precisely control the RF transistor's base voltage. This current mirror lets users simply choose a standard bias voltage to adjust the performance of that amp. Now, speaking of performance, let's move into some of the specifications of amplifiers that can be controlled with the bias. Now, some amplifier performance specifications are majorly affected, and some are relatively unaffected by the changes in those bias levels. The performance specs that are dependent on the bias condition are the saturated output power, gain, harmonic intercepts, 1 dB compression points, phase noise, and most directly, the current consumption. Now, the current consumption does have a direct relationship to that bias. Typically, these specs all show an increase in magnitude as you bias the amp more aggressively. The variables that are usually not affected too much by the bias conditions are the input and output return losses and isolation. The max safe operating conditions are also just dependent on the process by which the transistors are made. Now, because the bias condition is so important to the amp's performance, we don't want to consider the bias circuitry elements that we use in those circuits to be ideal. If we treat those bias components as ideal, then we would never have to worry about controlling the power supply noise and the feedback. Fortunately for us, these components are not ideal. So to control that supply noise and feedback, we typically want to use some bypass capacitors and series inductors. These components can be applied to your amplifier circuit, either on the chip itself or using some off-chip components. However, there are some careful considerations that should be made when choosing. The on-chip components have a few drawbacks. Now, one of these is the chip size. The capacitance and inductance of on-chip components is limited. The inductors are typically limited to blocking greater than 1 gigahertz frequencies because they use thin wires and there's a lack of magnetic material on chip. The on-chip printed metal lines are also only rated to handle a couple hundred milliamps of current. So they are not as useful in high power applications when you need hundreds of milliamps to drive your amps. The on-chip bypass capacitors are also limited in capacitance due to the chip size they require and their dielectric. With that being said, it's usually necessary to use some off-chip components to bias your amplifiers. Now, bias tees can be very helpful in this case because they can provide some large inductances that can adequately block frequencies below 1 gigahertz, and they can handle a large amount of current. Now, another non-ideality that should be carefully thought of is that amplifiers are not the most rugged of components. The amplifier's reliability is often overlooked, and there are a couple things that contribute to this, but one of the most important is heating. As the current flows through the junctions, heat is generated and then dissipated throughout the substrate over time. The better the amp can dissipate that heat, the longer the lifetime. Now, foundries typically do provide some data to demonstrate the predicted lifetime of their transistors. This data is usually shown in the form of an Arrhenius plot. This plot, provided by David Wang of Global Communications Semiconductor, shows the predicted mean time to failure for a given junction temperature. As you can see, if the transistors operated under the normal conditions, below 150 degrees C, you can expect the transistors to last at least tens of millions of hours. However, as you increase the junction temperature, the lifetime drops nearly an order of magnitude every 50 degrees. So it's important to ensure that proper heat sinking is used within your system if the amp is biased aggressively. Cooler amps are typically perform better and they last longer. Finally, sometimes people do misunderstand that the quiescent current that can be very different from the current in saturation. When operating with high input powers, the amplifier will typically draw significantly more current. Here in this plot, you can see the current consumption nearly doubles when operated in saturation versus small signal. And this is for one of our amplifiers, the AMM6702UC. Now with that, I'd like to take a moment to give you a short poll. And I'll let you all take a few moments to answer these questions. The questions are, what amplifier specifications are majorly affected by the bias condition? The answers could be output power, return losses, harmonic generation, and gain. The next question, what are some limitations of on-chip bias components? These are lack of magnetic material, current handling, size restraints, or all the above. And the last question, what is the best way to filter out power supply noise? And the answer and the possible answers there are bypass circuitry, input and output DC blocks, and sequencing and current mirrors. So I'll give you all a few moments to answer those questions. Looking like some good responses. Nice. Great. Alrighty, looks like most of you have had a chance to input your answers. So I'll go ahead and give you another 20 or 30 seconds here to answer these. Okay. Okay, so yes, the answer to the first question, what amplifier specifications are majorly affected by the bias condition? That is yes, output power, harmonic generation, and gain. Return losses are only very minorly affected, if at all. Number two, what are some limitations of on-chip bias components? The answer, the last one, all the above. Yes, that is correct. All three of these do limit the on-chip bias component effectiveness. And the last one, what is the best way to filter out power supply noise? Bypass circuitry. That is the correct answer there. Great. All right. Thank you all for taking a moment. And now we'd like to move along. We'd like to take a little bit of time to discuss some of the finer details of bias generation. There you go. If you can see, you can all see the results now. I'll leave that up if you care to take a look. Now, firstly, we'd like to discuss a critical aspect of bias generation, which is the importance of bypass circuitry. A couple of things a user should think about are switching time and noise filtering. As mentioned earlier, the bypass capacitors filter out the power supply noise and multi-stage feedback if you have a multi-stage amplifier. You typically should try to use multiple value capacitors to filter out a broader range of frequencies and prevent some resonance issues that can occur. However, the more you add, the more your switching time will be hurt. Using a bunch of capacitors will increase the charging time constants. So if the switching time is a concern to your application, then you should be careful to pay attention to how many you use. Now, as we mentioned, shunt bypass capacitances and series inductors act to limit the possibility of low frequency feedback oscillations in a multi-stage amplifier. But there is the possibility of some LC self-resonant issues between these inductors and bypass capacitors. To remedy this, we typically try to use some small resistors in series with the bypass capacitors to create a little bit of loss in that resonance loop and prevent an oscillation. For further information regarding the specifics of bypass capacitors, vendors do typically provide a lot of literature about their performance, but we don't claim to be experts with these. We just typically use them as they are recommended. Now, another key aspect of bias generation is the consideration of multi-stage amplifiers. Now, amplifiers are often constructed with multiple stages for higher gain. Each stage usually needs a supply and bias voltage to operate. So theoretically, the user could choose to bias each of the stages at a different level to possibly modify the gain, output power, and efficiency, etc. However, we typically do not break out each of the stages' supply and bias lines just for simplicity. To make it as easy as possible for the customers, we'd like to control the drain and the gate voltages with just one supply each. As shown here, this application circuit connects the drain pads to a single supply voltage, and we use 2 off-chip caps with a 10 ohm resistor. On the bias side, we resistively connect the gates because there is negligible current flowing. Then we connect the gate bias voltage to one of those pads. The third gate is chosen here, but in the end, it doesn't really matter which one you connect to. Now, another bias generation problem that we often see is how to step down an incorrect voltage rail to the level that's needed for the amp. This can often be a deciding factor in what amplifiers customers end up choosing because they don't want to spend that extra board real estate to adjust these voltages. However, there are some simple circuits that can be used to easily step down these voltages. To step down a supply voltage, step diodes are often your best bet. The amplifier current pull varies with input power, so we want to use diodes that will keep a constant voltage drop across them. The drop across resistors, if we were to use resistors in place of the diodes, the drop across those resistors would change if the current changes. So we don't really want to use them here because your bias point would be moving all over the place with the change in current pull. In the example on the left, we have a 12 volt supply voltage that's stepped down to the desired 7 volts using 5 1 volt step diodes. Luckily, on the base side, we can use resistive dividers to help step down that bias voltage. Now, this is because there's only a very small amount of current flowing through the gate of a FET, and in the BJT case, the current mirror controls that current. So it is okay to use a resistive voltage divider here to drop that bias voltage to the correct level. In this example, we use a 9 kilo ohm and a 1 kilo ohm resistor to drop a -5 volt bias rail to a -0.5 volt bias voltage. Now, the final bias generation issue that we want to touch on here is how to create a sequenced negative bias level. Like we said earlier, some amps need a sequenced bias and a supply voltage to avoid damage. One of our popular amplifiers, the AMM6702, is one of those such amps. To make it more user-friendly, we wanted to create a sequencing charge inverter circuit. The circuit is integrated into a module package, and the circuit diagram and BOM are released in a tech note listed here to allow our customers to design this into their own systems. The circuit diagram is shown here on the left, where a standard 5 volt voltage is applied to a commercial inverting charge pump, which then uses an oscillator and a feedback loop to generate a controlled negative voltage. That same positive voltage is also presented to the amplifier through a FET, which only turns on when you have a sufficient negative voltage presented to it. So what the circuit does for our customers is it allows you to apply just a single 5 volt voltage, and it takes care of the sequencing and negative voltage generation for you. This circuit can be made with off-the-shelf parts, and for further details regarding its function, please see the tech note listed below on our website. Now, I'd like to end today by giving just a brief description of our top-of-the-line amplifiers that we currently offer here at Marki. We have a positive-only bias, low-phase noise amp line that gives you great high power and high gain. We have our rugged and reliable ADM series that provides a medium power square wave and is a very good mixer LO driver. And we have our millimeter wave LO drivers. These are medium power LO drivers that we offer sequencing and negative bias circuits for to eliminate some of those unnecessary complexity in your design. The APM and AMM series amplifiers also come in a surface mount, bare die, and connectorized modules to simplify your production needs. All of these amplifiers do offer best-in-class performance, and we are always trying to push these parts to shatter the performance barriers. Now, for more information, we have multiple amplifier tech notes and videos on our website. And before we move into the Q&A, I'd like to inform you of some of our upcoming webinars that you may be interested in. Now, on April 30th, we have a brief guide to mixer spurs. This will be presented by Harley Berman and Christopher Marki. And on May 14th, we have high frequency packaging from the experts. And this will be also presented by Christopher Marki. There are registration links for those two webinars, and recording of this webinar will be provided to you through an email in the coming days. And with that, I'd like to thank you all for joining us. And we will be opening up for some Q&A with Rob and I. So thank you for coming out.
Cool. Thanks a lot, Jacob.